sits next to Liam.
Oh yeah, we're missing somebody over there. Oh, where's, oh, there she is. And then we're missing, that's Josh over there. So Josh is absent. But Sid's back. Woo!
Oh, yeah.
All right, so I'm on page 40 of my notes. Right? And we're not going to do every single one of these problems. I'm going to talk about, okay, so number 5, see the data points they give you, and they tell you to do a logarithmic regression. So, we're going to go to our calculator, right? We're not going to do this right now. You know how to do this. Put in your data points. Now, do you know which regression is the logarithmic one? Go to Stat Calc, go down the list. Which regression are you going to use after you get your data points in there? Log. Nope, don't use logistic. If we want, look, read the question. Compute a logarithmic regression. So you don't want a logistic regression. You don't want an exponential regression. LN. LN, what does LN stand for? Natural logarithms, right. So that's the regression button you're going to choose.
Wait, why wouldn't it be logistic? Because logarithmic regression model.
Okay, think of your BFFs. Are logarithms and logistic functions the same thing? No, the logarithmic function is this one. The logistic function is the one, they're two different functions. It's like, why do I not do a quadratic when it says to do a linear? Because it's a different function, right? So I gotta do the one it tells me to do. All right, so you know how to do that. You can do that on your own time if you want. I wanna look at number 6. We gotta match the function with its graph. So, let's not forget that the basic logarithm looks like this, right? Now, take a look at, let's say, the second equation. That is an easy one. What has happened when we have x plus 1? What does that do to my picture? Moves it left 1. So which graph is this one exactly, except left 1? B. That's B, right? That's an easy one. Now, let's look at the third equation down. Now, what has happened in the third equation down? It's been moved 3 to the right and turned upside down. So when we take a logarithm and we turn it upside down, that is over the x-axis, we get a shape that looks like this, right? So do we have one that has that shape but is moved 3 units to the right? That would be A. All right? Now, I want you to look at the first equation. Now, the first equation, the x has been made negative. Okay, wait a second. What does that do? If the x is made negative, that takes your picture and mirrors it onto the other side. So you're going to have, instead, go back to my original. So instead of having that, you're going to have something that looks like this, right? But in addition to that, there's a 1 in there. Would you agree that for the first equation, the asymptote would have to be at 1, at x equals 1? Yes, because you can't take the logarithm of 0, right? 1 is the cutoff. So there's gonna be an asymptote at 1, and it's gonna be a backwards picture. So which one is that? D? Has an asymptote at 1, and it's back, this way. All right, so that leaves, the only equation we haven't talked about is the last one. There's all kinds of stuff going on in that last one. Where's the asymptote in the last equation? At 4? Okay, we all need to get that. The asymptote's at x equals 4. And the x is negative, and the function is negative. So that means not only have we flipped it this way, but we've turned it upside down, and it has an asymptote at 4. Well, which picture is that?
C.
C. All right, so we just kind of walked through those problems. Everybody making sense out of that? Okay. 3.3 will be due on Wednesday. And let's take a look at 3.4. Properties of logarithms. You guys already know these. Last time I talked to Mr. Miller, he told me you were masters of your properties of logarithms, so I'm gonna spend a lot of time on them. We just need to remember what it says here on the paper. When we take the logarithm of a product, we add the logarithms. So that's what that means. The logarithm of a product is the sum of the logs, which is not a foreign concept to you, because when two numbers are multiplied, their exponents are added. When two numbers are multiplied, their logarithms are added. The properties are the same. So in the division problem, the properties would be, or excuse me, the logarithms would be subtracted. And one of these we've already used. If you have the log of, I use their letter, the log of r to the c, that exponent comes out in front, so c log r. And that's true of any base. The base is irrelevant, so any base that works for it. So let's see if we can do some of these real quick. Expand the following. The log of 100x. Okay, so test, these guys are being multiplied right here, right? So if I'm gonna expand this, what's that gonna look like? The log of
100 plus the log of x.
plus the log of x. Now, if this were some base other than 10, I'd be done. But what's the log of 100? 2. The log of 100 is 2. Mrs. Ford, how am I supposed to know that, guys? The log base 10 of 10 squared is 2. So 2 plus log x is the answer to that one. Now all you're doing is expanding, so what's the expansion for that one? Ln x to the negative second would be, Lucy?
Negative 2 ln x.
Beautiful. And there's nothing else to do with that, that's just it. How about C? Log 2 minus log y, nothing else to do with that one. Oh, what about D? What is going on in D? Well, first of all, radicals don't get along very well with logarithms. They don't get along very well. So every time I see a radical in logarithm land, I'm going to change it into an exponent. So this is the same as x over y to the 1/4 power. And then that 1/4
Goes to the
goes out in front. And then becomes a subtraction. So I don't care if you do this or if you do this. It doesn't make one single bit of difference. The 1/4 does go with both pieces, right? So here I got it in parentheses, and here I've distributed it. I don't care which way, it doesn't matter. But the 1/4 has to somehow be attached to both of those.
Can we put the whole thing over 4?
Yeah.
Okay.
All right, what about E? We're just expanding it. So that'll be what? So log 10, which somebody's already said is 1. So log 10 plus what?
Log X.
Log X squared, which will be 2 log X. You can do that in 2 steps if you need to. You can do it in 1 step if that makes sense to you. Plus
4 log Y.
4 log Y. And then I'll make that so it's completely expanded now. All right, last one in that section. First of all, that's gonna be a subtraction, isn't it? I think I'm gonna start with that, because there's a lot going on here.
Could you make it
So then, again, radicals just don't work in logarithm land. So I'm gonna think of this as x squared plus 5 to the 1/2. And then I can always pull my
exponent?
exponent out. So 1/2 ln x squared plus 5 minus ln x. Nothing else you can do. Stop. There are no properties of logarithms that deal with sums. In other words, you can't like distribute this or anything. You are done. You're done right here. Tess?
So you can't do like ln, or you can't take out the x squared and put.
Nope, because these two are not separable. That's a sum. You can't do anything with a sum, except leave it. If, Tess, if that exponent, hey, if that exponent was up here, then I can pull it out. But I can't take the logarithm of just the x part, so that's finished right there.
If that exponent was out there, outside the parentheses, you multiply that by 1/2.
Yep. It would cancel then. All right, part 2 here is just the opposite. So we need to put them together. I think one thing that goes without saying is, I didn't say it, maybe I should. If you're gonna put them together, they have to have the same base. You can't have a base 3 and a base 4 and combine them, okay? So all the bases have to match. So we've got logarithms here, so what do we got? This is gonna be the log of what?
X over Y squared.
XY squared, awesome. And where does that squared go? Only on the Y. Only on the Y, perfect. How about B? Yeah. Mr. Mello was right, you guys are geniuses. Okay, how about this next one? There's a lot going on.
Log XY to the 4th.
Log XY to the 4th minus log YZ to the 3rd. That would be my step 1. You might do more than that, but is that okay?
Can you distribute that exponent, or would that?
Absolutely can't distribute that exponent. I'm not gonna do that yet, but I'm going to in a minute. First, I'm gonna somehow put these together. So what's this gonna be? The log of
XY
xy to the fourth over yz to the third? Now we know that if there were a plus right there, then we can't distribute that form. That would be like a giant foil deal. But since that's a times, we can write that as x4, y4 over y3, z3. And then we can cancel, and we're left with log x4y over z cubed, is that right?
Wait, how did the lines? Oh, I just.
Bless you. All right. Next, all right, what are we gonna have here? ln x to the fifth minus ln xy squared, which will become a division. So ln x5 over xy squared. So ln x5 over x squared y squared. So I heard somebody say ln x cubed over y squared. Now we got some interesting ones. True or false? I'm gonna give you about 3 minutes. Look through those, take a stab at them, and then let's come back and compare answers.
I think it's true. It's just squaring it. E has got to be false.
Sorry, you said what?
Who else?
It's true or false? It's written the way I wrote it.
I don't know, dude.
E is true.
Which stuff is done? How many truths did you
Because
get?
wouldn't it just be two? Because I feel like it's
Anybody else have them all done? How many truths did you get? 4 truths? How many did you get? 3 truths? So we got 5, 4, and 3 truths, okay. You got 4?
Did you say H was true?
4 truths? All right, let's hash them out. Here we go. 3A. False. That right there is the biggest mistake that I see. When you get into solving these equations and you start trying to figure things out, kids always want to distribute. ln does not distribute. log does not distribute. It is false. False, false. Okay, what about B? True. That one is true, true, true. Absolutely. Everybody okay with that? All right, what about C? False. False. If you were going to simplify that, it would not become a division, it would become a subtraction. So that's a false. What about D? D is a false. Because there's a difference between this and this. This is the right side of the equation. Log base 5x times log base 5x. The left side of the equation is 2 log base 5 of x's. Those are not equal. So D is a false. What about E? That's a false. That 7 does not come out in front. That actually becomes a sum, right? The log base 3 is 7 plus the log base 3 of x. So that was false. How about F?
True.
That's a true. What about G?
True.
That's a true. And what about H?
True.
That's a true, that's a true, that's a true. 4 is 4, right? Whether it's inside absolute value or not, 4 is 4. X is an unknown, so absolute value is necessary there for that one. So that is a true one. All right, everybody okay with that? I think those are fun exercises. Okay, number 4. Now, things have evolved so much over all the last many years. Remember, when I was doing all this, I didn't even have a calculator. So when I had to find the log of something, we had to look it up in what's known as the CRC table, a big table, a book. And we had to look everything up and then do all the calculating by hand. Well, then the calculators came out and they have logarithm buttons on them, right? The 2 logarithm buttons are mine. Mine's an old calculator, so the 2 logarithm buttons I have are LOG and LN. The newer calculators, they have other bases. They allow you to pick whatever base you want. Well, we're gonna pretend that's not the case. And we're gonna look at how we can use a standard scientific calculator or an old grapher like I have to find the log base 3 of a number. Because this is not LOG. I'm not gonna hit LOG 19. That would be log base 10. I'm not gonna hit LN 19. That would be base E. So I wanna figure out how can I use a regular scientific calculator or my calculator to find the log base 3 of 19. Well, it's actually very, very simple. If I change this into its exponent form, I would have 3 to the x equals 19. Would everybody agree with that? And then it's an exponential, so I'm going to take the logarithm of both sides. And that will allow me to pull the x off. So x ends up equaling the log of 19 over the log of 3, which I can type in on my calculator. But let's look up here. This is also x. So basically what we figured out is that if I need that number on my calculator, all I have to do is divide the log of 19 by the log of 3. So the log of the big number divided by the log of the little number, or when I'm talking about this in some of my other classes, I say, when you write this, that one's on top of this one, or it's above that one, so this one goes on top, this one goes on the bottom, log 19 over log 3. Now, just for fun, type that in. There's nothing special about it, I just want you to do something else. So type in log 19 divided by log 3. Now, suppose that instead of logging both sides, I would have ln. Type in ln 19 over ln 3. Does it matter? Nope, it never does. You can use whatever base you want. This is called the change of base formula. If you do not like the base you have, you can change it into base 10 or base E or whatever base, what's your switch. So when I look at the next one and it says the log base 4 of 7, you can go through all this if you want, but you don't need to. The formula says that's going to be the log of 7 divided by the log of 4. And the last one's going to be the log of 17 divided by the log of 0.5. Everybody okay with that? So if you have an expression that's in a funky base, just go ahead and do your change of base, and that will work. All right. Number 5, rewrite using natural logarithms. So what does that mean? Natural logarithms means
ln.
ln base e, right? So basically, aren't we just changing the base now to e? So what would this be? ln x over ln 13? Or 3? Is that a 3? Oh, yeah. Sorry about that. It's not a 13, it's a 3.
Okay. Wouldn't that just like absolutely completely change the answer?
Nope. We just did it here. We just went through it. We're just doing,
Right. But
here
like,
I changed it into base 10. But I could have changed this problem right here into ln 7 over ln 4.
but like log and the natural log have different different bases.
Yes.
So how would you get the same value from
Okay, so let's come back over here. So after I rewrote my equations, the exponential, I took the logarithm of both sides, right? And worked this out, okay? It will also work if instead of logging both sides, I ln both sides. I can take whatever base I want. And because it's both sides are now ln's, the ratio is gonna be exactly the same as it was when it was a log. It's like saying, if I have 5 to the x equals 25 cubed. And I change this into, leave this 5, change this into 5 squared, I'm gonna get x equals 6, right?
Mm-hmm.
Well, if these were 3, if this was a 3, and this was a 9, because these numbers had the same relationship to each other as the 5 and the 25 did, is that because now that's a 3 and that's a 9, is that gonna change the answer to my question? Am I still gonna get 6?
Yeah.
Same idea. Same idea. As long as the bases are the same. So LNing both sides, LOGing both sides, you're not gonna change your answer. Okay? Where am I? Okay, B. Keep in mind that that problem says the log base 10 of x, that's the original problem. So what will that be in terms of natural logarithms?
ln x
ln x
over ln
ln
10.
x over ln 10?
You try.
Now, right now, you're sitting there thinking, why are we doing this? This is dumb. Why are we doing this? I'm telling you, when you get to your differential calculus and you start differentiating and integrating, you're gonna be happy that you can change your things into LNs. Because there are formulas, rules that you will memorize for E's and LNs that you're not gonna memorize for base 5 and base 10 and other bases. You're gonna want to rewrite things in terms of natural logarithms. And it's easy to do. ln that over ln that. Done. Okay, last one. What's that one gonna be? All right, so don't make it hard. It's super simple. It's gonna be ln
C
C
divided by
minus D over ln 5. Now, can you do anything with ln C minus D? Nope, so that is done. Done, done, done. Now, I have probably led you astray. Because I remember distinctly telling you, when we were doing our BFFs, that this was the logarithmic curve. And we memorized it as y equals ln x, that's the way we memorized it, but y equals log x looks the same way, y equals log base 5 looks the same way, but this one looks a little different. Because now the base is less than 1. So think about that for a second. Think about what impact that might have on the graph.
Would it make X negative or something?
Think about the inverse of this is y equals 2 to the x. Which looks like this, and then the logarithm looks like this. Those are inverses, right? What would the inverse of this be? Would it be y equals 0.5 to the x? And what does that look like? Y equals 0.5 to the x.
Gets smaller and smaller.
Now, that's not this. This is the inverse. This is the inverse. So that will be, that's a decay problem. So won't that look like this? So what would the inverse of that look like? Remember, the inverse is the reflection across the identity line. What's that gonna look like? Tess?
I have a question.
Uh-huh.
Where did you get 0.5 to the x out of log 0.5 to x?
Okay, no. Okay, so this is the problem, but we're trying to figure out what it looks like without a calculator. So I chose, may not be working for you, but I chose to go back to what I knew. I knew this picture looked like that, and I know its inverse, this is its inverse, looks like this.
Wait, how do you know it looked
How do I know what looked like what?
like log 2 to the x?
These are my BFFs, sweetie.
Oh.
They don't go away. They're part of our lives forever, okay? So we know that, right? So, what I'm hoping to be able to do is graph the inverse, okay, so I know what the inverse looks like. This is the inverse of what I want, and I know it looks like this. So I'm hoping that I can get what I want by simply graphing the inverse of what I've already graphed, okay? So that's where we are now. We're trying to figure out what would that look like.
Wait, for the inverse of y equals log half x, how do you know that that is what that part of the inverse would look like?
Okay, I haven't graphed anything here yet. All I've done is graph this exponential.
Yeah.
Okay, well, that was in an earlier lesson in this chapter, when the base is less than 1, it's a decay problem. So the exponential looks like that, right? So this what I drew is this picture. Now I'm trying to figure out what its inverse looks like.
It's gonna have an asymptote at y equals 0.
So it's gonna have an asymptote at y equals 0 because this is x equals 0. Or actually, this is y equals 0, so
Other
its
way.
asymptote is gonna be at x equals 0. All right.
It's gonna kinda. It's gonna go like this.
Does that come to right, Oliver?
It's gonna be kinda like this.
Come to right. Check it out and see. If you're struggling with what it might look like, could we plot points? Could we do that? Let's see, go ahead, he's gonna sketch it in. So there's his idea. I'm gonna go ahead and put that in orange so we can see. Now, to see if Oliver's on the right track, this exponential? Well, I know that point is 0, 1. So what point has to be on this one? 1, 0. All right. What are some other points? If x is 1, y is 1/2. So we have to have 1/2 1 on the picture. So far it looks good. If x is -1, we get 2. So this is -1, 2. So we need 2, -1. I think he's got it. It's not perfect, but it's pretty darn good. Good job, Oliver.
Can we go back to how you knew there'd be a vertical asymptote at y equals 0?
Because there's a horizontal asymptote right here at y equals 0. And when you do the inverse, x and y switch. So what was y equals 0 becomes x equals 0. Now, one thing that's a little clear out of this is that we don't really have a good command of what these basic things look like. And we need to. All of us need to. Because now what we're gonna observe, because we still have, look at these graphs in number 7, look at those equations. We have to figure out what in the heck's going on. What did we just observe? Well, we did it through inverses, but if the base is above 1, then we have a regular logarithmic picture every time. If our base is less than 1, that's what Oliver drew. It looks like what's happened. It's kind of been flipped across the x-axis, hasn't it? Isn't that what's happened? Does that make sense at all? That the picture essentially got flipped across the x-axis. Does that make sense? I want you to look at something here. Okay, this is the inverse. I'm not doing the inverse now. This equation right here is the same as this. Would you agree with me? This equation, which is the one we were graphing, is the same as this. Would you agree with that? Now, what's 1/2? Isn't 1/2 2 to the -1st? So isn't this equation, first it was this, and then it was that, and now it's this, aren't these the same thing? So compare that one to the original, and what happened? We changed the sign on y, and when you change the sign on y, what do? Flip over the x-axis, so it all makes perfectly good sense when you stop to think about it. Really think about it. Okay, so with all that in mind, take a second with your partner, your table mate there, and see if you can match up these without trying to do it on your calculator. Ken, look at the parentheses, that's gonna tell you where your asymptote is, right? The parentheses is gonna tell you where your asymptote is.
This one has math choice.
Oh, C, sorry, I was looking at, so which one?
We should have
actually 44 and 46. So yeah. So we need to understand if they're growth or change. So 43 is going to be growth. Yes. It's going to be growth. It's going to have that for the 2. So I think 43 is way so this one's 43 is going to have because the base is right at 1. So I think you see what I mean?
Wait, Mrs. Ford?
Yep.
Would you say C has an asymptote at x equals 3 or x equals 2?
Well, we still haven't gotten any questions solving it.
Alright, I'm going 44C.
Well, yeah, because it's growth.
Okay, wait, well,
All right, have you sorted it all out? So I heard somebody say process of elimination. Nothing wrong with that. One of these, guys, which one of those problems, 43 to 46, is the easiest? 44. Hands down, everybody knows that 44 looks like which one? C. It's a standard thing, everything's bigger than 1, no issues. C. Which of the other equations has an asymptote at 3? 46? So the only other picture that has an asymptote at 3 is A? So which one is that? 46? 46 is A. Is everybody okay with that process of elimination?
yeah.
All right. So then that brings us to problem 43 and 45. Now, I don't know how you thought about this, but 45 is what we just talked about. 45 is going to look like Oliver's picture, only shifted 2 units to the right. So I think 45 is which one? D? And if 45 is D, then 43 has to be the only thing left, which is B. Has the asymptote at 2, and has got some flipping around going on because of the negative x. Easy enough? Alright, I would definitely remember this idea that when the base is between 0 and 1, when the base is less than 1, you're going to get the upside down picture because of this phenomenon right here, the y's changing sign, when the base is less than 1. Okay? All right. Guess what? 3.4 is going to be due on Wednesday also. I know you went for days without having homework. Well, now you've got homework, so here we go. We're going to do a couple more, and then we'll stop for the day because we've done a lot today. Give you a couple minutes to get started on your homework. But we need to start solving some equations. So let's get the first 4 done, and then I'll stop. All right, so here we go. We're gonna solve these equations. So, how about the first one, doing this without a calculator? If we can, I don't know, let's see. What are we gonna do here?
We can multiply the
Divide by 20.
Divide by 20. So 1/2 to the x over 3 is gonna equal what? 1/4. Oh, that's nice. Because what do we know about a fourth?
it's 1/2 squared.
It's a half squared. So since these are now both halves, we can say x over 3 equals 2 and x equals 6. Now, if this number had been, let's say, an 18, we would have started by dividing, right? But then we would have needed our calculator because we would have needed logarithms to solve it. But since we could get the bases the same, didn't need a calculator. All right, what about this guy? He's a logarithmic equation. 2 to the 5th, beautiful. 2 to the 5th equals x minus 1.
32.
So 32, would you say x is 33? That was easy, as long as we remember 2 to the 5th is x minus 1. Good, put your hand up.
Yeah, how did the log just disappear?
We didn't, we rewrote it. This in its exponent form, remember the log ruling thing? 2 to the 5th equals x minus 1. All right, how about this guy?
4 to the x over 2.
4 to the x over 2 equals 32.
Ooh.
You can do 2.
4 to
Use
the-
2.
Oh.
32 is not a power of 4, but 4 and 32 are both powers of 2. So 2 squared to the x over 2 equals 2 to the 5th. So what happens here?
Equals plus.
So that becomes 2 to the x. Would you agree with that? And therefore x equals 5. Now if you're doing these like in homework or something, you could always check that on your calculator. If you took 3 times 4 to the 2.5, you should get 96. All right, last one, here we go. What's this gonna be? 4 to the 1st equals 1 minus x. So it looks like, oh my, x is negative 3. All right, back to 1